this video, we are going to discuss about the data pre-processing. We know how we can improve the performance or performance of the neural network, right? But still, we should have a clear understanding about it. So this is the video that will explain about different data pre-processing techniques. So basically here we will see how do we do the scaling or normalization in deep learning, right? So this is what we are going to see over here, right? So here you can see original data, and here I have shown some figures. Now first let us try to understand the data first. Okay, so what I'm going to do now is right, so I'm going to take some random numbers now. Okay, so let me make it very clear to you. So the first step is that we are going to import NumPy library. So import NumPy as NP, right? So in the second step, what I'm going to do is I'm going to create some random numbers of 10 cross 4 shape, which means I need 10 rows and 4 columns. So let me give some introduction, like why we are doing this. So like say, assume we have like n into d. Here, say when we handle MNIST data set, there are say 10,000 images, and this basically tells us about the dimension. So when we talk about dimension, it was like 28 into 28, that is 784 pixels, right? So what we did was it was having the images were of 0 to 255. So we divided it by 255, and we made everything to range from 0 to 1, right? So that idea, we are clear with that. So the same thing we are going to look into it within the scientific way, right? So what I have done now, I have created 10 cross 4 random numbers, right? Random numbers, clear? So what is this random dot rand? Let's study about that. So it will give some random values in a given shape, and it will populate random samples from a uniform distribution, right? So that's very clear, which means the values ranges from 0 to 1, right? So I have taken some numbers. So what I'm doing now, I want to compute mean for that. So I'm writing mean is equal to np dot array and np dot mean x comma x is equal to 0, right? So let me compute the mean now. So whenever we write x is equal to 0, that stands for the rows. So I'm getting the mean now. So what does this mean for these 10 data points, right? So this will be the corresponding mean. The next set of 10 points, this is the corresponding mean. This is the corresponding mean. This is what happening over here, right? So what I have done now, I have computed the mean. So first I have created random numbers of shape 10 cross 4, and then I have computed the mean of it, right? So what I'm going to do now is I'm going to repeat the mean numbers. So you will come to know why I'm doing this step, right? Okay, so what is happening over here? You can see that 0.43229898, right? So that the same number is present in all the rows, right? So the next one, the same numbers. Next one, the same, right? So why I am doing this, that I will tell you shortly, right? So what I'm going to do now is I'm trying to compute x minus mean underscore repeated. Mean underscore repeated is nothing but the mean values are repeated, because basically what I'm trying to do over here is I'm trying to compute x minus mu. See, it's very simple, like 1, 2, 3, 4, 5. What is going to be mu in this case? So definitely mu is equal to 3, right? So what x minus mu means, what do I do? 1 minus 3 is minus 2, 2 minus 3 is minus 1, 3 minus 3 is 0, 4 minus 3 is 1, 5 minus 3 is 2. So I have done the same thing over here, but I had 10 cross 4, right? So 10 cross 4 elements I had, and I have computed the mean of it. Now I have 10 cross 4 elements. So I want to subtract this from this, right? I want to subtract this from this. That is the reason I have duplicated or repeated the mean values, and then I have done the calculation, right? So this is one kind of data pre-processing technique, right? So let me see that. Okay, so you can see the values now, right? So what has happened over here? It is doing x minus mu, right? So so what I had actually 0.3596141, and if I subtract it from subtract this and that what is that x actually 0.3596141 minus this number 0.43229898, I'll be getting this value, right? So the same thing is done for all the cases, right? So now the next step, what I'm doing now is I'm trying to find out the standard deviation, right? So std is equal to np.array and np.std, and I want to find out the standard deviation for x, right? So when I execute this code, I'm getting the standard deviation, right? So I'm getting the standard deviation. So what I'm doing now, I'm going to follow the same procedure that I did for mean. So I'm getting the same values, right? You can see that 0.2198493. So I'm getting the same values over here. So what I'm going to do now is I'm going to do x minus mu divided by sigma. Yes, we know that, right? So this is not new to us. We have studied this in machine learning, right? So the same concept I'm applying it over here. So you can see that x, what is the x actually? X is nothing but x minus mean underscore repeated, which means what? X minus mu, right? So x minus mu divided by sigma, right? So this is what I got as the output. So what will happen every time you execute it again and again? What may happen? Like each time it may take different random numbers. So I may get different values, right? But the concept is the same. Is that clear? So this is one of the main data pre-processing technique. So let me also help you to understand with the help of this article, right? So this may be helpful to you to understand it in a better way, right? So let us try to understand about this, right? So pre-processing for deep learning from covariance metrics to image whitening, right? So let us try to understand this. Pre-processing refers to all the transformations on the raw data before it is fed to the machine learning or deep learning algorithm, right? So for instance, training a convolutional neural network on raw images will probably lead to bad classification performances. So the pre-processing is also important to speed up training, right? So there are several techniques like centering and scaling techniques, right? So like first we will see about the background. So we will get background in the sense like what are the concepts associated with this data pre-processing, like variance, covariance, right? And the second one is about the pre-processing, like what are the pre-processing techniques. That is what we have seen in the Python implementation, mean normalization, standardization, and whitening, right? So actually we are going to focus on this mean normalization, standardization part, right? So let us directly jump into the second one, right? So let us try to understand that mean normalization. Mean normalization is just removing the mean from each observation. So what has happened? X minus mu we have seen here, there. So it is like x minus x bar, right? So mean normalization has the effect of centering the data around 0, right? So we will create the function center to do that, right? Okay, fine. So the next part is about standardization or normalization. Standardization is used to put all features on the same scale. So each zero-centered dimension is divided by its standard deviation. So x minus mu divided by sigma, generally we say here x minus x bar divided by sigma x. Sigma x is nothing but the standard deviation of x, and x bar is the mean of x. Right, the next one is about whitening. So whitening or sphering means that we want to transform it to have a covariance matrix, that is the identity matrix, -1 in the diagonal and 0 for the other cells. -1 in the diagonal or the 0 for the other cells. So it is called as whitening in reference to white noise, right? So let us try to understand this. Whitening is a bit more complicated than the other pre-processing, but we now have all the tools to do that, right? So we will be zero center the data, we will decorrelate the data, we will rescale the data. So what is the zero centering? This means like this refers to mean normalization, right? Mean normalization. That is what we have seen, right? X minus mu. So this is about that case, right? Fine. Yeah. So the next one is about decorrelate. Like here, what we do is like we need to decorrelate our data. It means that we want to rotate the data until there is no correlation anymore. So now if you look into this, this is how the data was looking like. And this plot is showing us the correlated data. So if you take a data point with a big X value, then chances are that associated Y will also quite big, right? So that is very clear, right? So now take all the data points and do a rotation at least by 45 degree, or we can rotate, 45 degree, we have to rotate it counterclockwise. The new data plotted on the right is not correlated anymore. So you can see that big and small Y values are related to the same kind of X values, right? Fine. So the question is how we find that right rotation in order to get the uncorrelated data, right? So actually it is exactly what the eigenvectors of the covariance matrix do. So they indicate the direction where the spread of the data is at its maximum. So the eigenvectors of the covariance matrix give you the direction that maximizes the variance. So the direction of the green line is where the variance is maximum. Yes. So just look at the smallest and largest point projected on this line, the spread is big, right? So compare with that on the orange line. So here we can see that the spread is very small, right? So we can decorrelate the data by projecting it using the eigenvectors. So this will have the effect to apply the rotation needed, and we can remove the correlations between the dimensions. So how do we do that? We have to calculate the covariance matrix. We have to calculate the eigenvectors of the covariance matrix, apply the matrix of eigenvectors to the data. So this will apply the rotation, right? So now let's try to decorrelate our zero-centered matrix. So now that part is clear to you. Now this is the first part, and now you can see that, yes, is that clear now? So the covariance matrix, now a diagonal matrix, confirms that the covariance between the two dimensions is equal to 0. Very simple. So the next one is about rescale the data. So the next step is to scale the uncorrelated matrix in order to obtain a covariance matrix corresponding to the identity matrix, right? So what do we do here? We scale the uncorrelated matrix to obtain a covariance matrix corresponding to the identity matrix. So to do that, we scale our decorrelated data by dividing each dimension by the square root of its corresponding eigenvalue, right? So we can see that the covariance matrix, that this is all good, right? So we have something that looks like identity matrix identity matrix 1 on the diagonal and 0 elsewhere, right? 1 on the diagonal and 0 elsewhere. Clear? Right. So the next one is about image whitening, right? So in image whitening, we will see like how whitening can be applied to pre-process an image data set, right? So here, first we have to load the images. So C4 data set is taken, and this is available in Keras, right? So you can take it from there. It has around 50,000 images. The shape of the training data is 50,000. 32, 32, 3. So 32 and 32 corresponds to pixel, and 3 stands for the dimensions, that is red, green, and blue, right? So each value is of the brightness of the corresponding color between 0 and 255, right? So now we will be selecting a subset of the images, say 1000, right? So 1000, 32, 32, 3. 32 and 32 stands for Yeah, pixel. And then this 3 stands for the, yes, you're right, dimensions. So now we will reshape the array. So we have to flat the image data with one image per row. So the image will be 1,3072. So what is this 3072? 32 into 32 into 3, right? So the array contains all the images will be 1000, 3072, right? So the next step is to be able to see the images. So the function imshow, right? So this will help us to look into the images. So this is how the image look like, right? So now we can implement the whitening of the images. So the first step, we have to rescale the images, which means like we have to obtain it in the range of 0 to 1 by dividing it by 255, right? Now, like a data minus minimum of data and maximum minus minimum, right? Like this we have studied in machine learning, like x minus x minimum divided by x max minus x minimum, right? Clear, right? So now here the maximum, the minimum value is 0. So what will happen? We will have only data divided by maximum of data, that is nothing but 255, right? So when we do this mean subtraction, is it per pixel or per image, right? So, okay, cool. The range of our pixel value is between 0 and 1 now. So the next step is that subtract the mean from all the images, right? So one way to do it is to take each image and remove the mean of this image from every pixel. The intuition behind this is to center the pixel of each image around 0, right? So that's what our aim is. So another way is to take each of the 3072 pixels that we have for every image and subtract the mean of that pixel across all images. So this is called per pixel mean subtraction. So this time each pixel will be centered around 0 according to all images. So when you will feed your network with the images, each pixel is considered as a different feature. With per pixel mean subtraction, we have centered each feature around 0. So this technique is commonly used, right? So now we will do per pixel mean subtraction from our 1000 images. So our data will be organized with the dimensions images comma pixels, right? So now we will have 1000 comma 3072 because we already calculated that 32 into 32 into 3 is 3072, right? So the mean per pixel can be like 3072, right? So this gives 3072 values, which is the number of means 1 per pixel, right? So let us see over here. So this is near 0.5, right? So we already have normalized that. So that actually we have normalized it to 0, 1, right? So however, we still need to remove the mean from each pixel, right? So now this is not exactly 0, but it is small enough that we can consider that it worked, right? Now, right, so you can see that, right? So it is not actually 0, but it is small. So now we want to calculate the covariance matrix of the zero center data, like the previous case. So we can calculate it using np.co, right, from numpy function. So our variables are our different images. So this implies that the variables are the rows of the matrix X. So we have to be very clear that we will tell this information to numpy with a parameter row var equal to true, even if it is true by default, right? So now the magic part is that we will be calculating the singular values and vectors of the covariance matrix and use them to rotate our data set, right? So now you can see that like we had a lot of images and we were using only 1000, right? So like that is what even I have done because I do not want to use everything. So I have done only this person has taken only 1000 images, right? So that can be like you can see the formula now, like u dot diag 1 divided by square root of diag of s plus e ut dot x. So what is this u? That stands for the left singular vector and s stands for the singular values of the covariance of the initial normalized data set of images, and x is the normalized data set, and this is an hyperparameter which is called as the whitening coefficient, right? Okay. So now we will try to implement this equation, right? So let us check the dimensions of this. So here we can see that S is a vector containing 1000 elements, the singular values. So diag of S will be of the shape 1000, 1000 with S as the diagonal, right? So now this is also the of the shape 1000, 1000 as well as U and U bar T, right? So we have also seen that X as the shape 1000, 3072, right? So this is what we are getting now. Now you can see that. So why we are getting this way? Because this is not rescaled. We have not rescaled the pixels and there are negative values. So to do that, we can put it back in the range 0, 1 with the same technique. And now you can see that, right? So it looks like an, it's perfect, right? So for different learning rates, different hyperparameters, it is being worked for 500 images, 2000, 5000, 1000, right? So the result of the whitening is different according to the number of images. Can you see that 500 and this is for 2000? Now check for 10,000 images, right? So, and also it depends upon the value of the hyperparameter, right? Because 0.1, 0.01, 0.001, right? So the image on the left is actually the original image, and whatever we got is like a whitening image, right? So this is really a cool article, and I think you clearly understood the concept on data pre-processing.